be delivered online this coming Friday from 7 p.m. to 8:30 p.m. So the question will be given through WebAssign, but you are expected to write detailed solution to every question and submit the question, upload the question as a PDF file on Canvas. So there won't be anything to input on WebAssign, just the question will be delivered through WebAssign, but all your answers, they have to be like on paper, scan and upload to Canvas. So when the questions are released at 7 p.m., in order to avoid any like disconnection problem from the website, I would advise you to save all the question in a PDF file or a Word file. So in case you get disconnected from WebAssign, you can still see your question and work on the model test. At the end of the test at 8:30, you have half an hour to actually scan your work and upload it to Canvas. This will be a strict half an hour. So if you submit at 9:01 p.m. instead of 9:00, your test will be rejected. So like keep in mind this half an hour extra is just for scan and upload and not to work, like not to spend an extra half an hour working on your solutions. Any question before we jump back into the course?
Yep, good morning. I have a question. Is it compulsory to use the engineering paper?
It's better. So use grid paper at least, because there will be some schematic to do. And if you use just plain papers, they will be dirty. And as if we cannot understand your schematic because it's too dirty, then you won't get allowed any mark.
How many questions are on the module test?
3 to 4.
Do we need to explain why we use formulas on the formula sheet like we do for question 7 and the weekly assignments?
Yes. Every formula you use, you have to explain why you use this formula.
Even if it's on the formula sheet?
Even if it's on the formula sheet. The formula
sheet
is here to help.
Can it be like a simple, like, I'm using this formula because I was given these values and these values are in the formula?
Like, for example, if you have to calculate the force between 2 point-like charge, okay, you say like the force between 2 point-like charge is given by this formula that I take from the formula sheet, therefore I use it to calculate this force.
Okay.
But you cannot just like pick like randomly a formula and use it. Okay, if you do not explain why you use this formula, you won't get allowed. You won't get full mark. You will get partial mark only. Any other question? So if you have any question before the test, just drop me an email to me or any of the other instructors, so Professor McWilliam or Professor Tui, and we'll be happy to answer all of them. All right, so now let's jump back to the lecture. So before we move to sources of magnetic field, we're gonna finish the chapter on magnetic field and magnetic forces. So now let's jump into application. So the first application I will talk about is the Hall effect. So what is the Hall effect? So if you take a piece of conductor, so here you have a rectangular piece of metal, and you have a current flowing through it. So here you have a current flowing to the right, and you put this piece of metal in a magnetic field, a constant magnetic field. So here's a green arrow. Well, you have moving charge. So those moving charge, they will experience a Lorentz force. And as a result, they will move into the metal, and you will end up with an excess of negative charge on one side and positive charge on the other side. So this is given by the Lorentz force. So if you look here, so if you take a negative charge, so velocity is this way, magnetic field into the page, so your thumb is going down, but because it's a negative charge, it's pushed up. As you can see, all your electrons will be pushed up, but because a piece of metal is finished here, you will end up with an excess of negative charge on the upper side of your piece of metal. If you have an excess of negative charge in the upper side, that means you will have an excess of positive charge on the other side. This results in an electric field. And basically at equilibrium, you will have the magnetic force that will balance the electric force. So now your current is actually flowing horizontally in the piece of metal. If you have an excess of charge on one side of the conductor with respect to the other, then you end up with an electric potential difference. And if you end up with a potential difference that you can measure with a voltmeter. Okay, so the charge carrier in a metal, they can be electrons or they're mostly electrons, but it's not. You can have conductor where you can also have positive charge carrier. So let's study this in a bit of detail. So each moving charge in the conductor experiences a magnetic force. So you remember the formula for the magnetic force is QV vector cross the magnetic field. So in this configuration here, you see like the velocity is actually perpendicular to the magnetic field. So you end up with a magnitude of the magnetic force equal to the charge of the charge carrier, the drift velocity times the magnitude of the magnetic field. So the positive and negative charges, they move in the opposite direction, which lead to charge separation and consequently an electric field. Okay, so that's what I was saying here. For example, you will end up in electron pushed up and positive charge carrier pushed down. At equilibrium, the magnitude of the force due to the magnetic field is equal to the magnitude of the electric force. Okay, so if you have here negative charges, here positive charges, then you have an electric field, so from the plus side to the minus side. And this, of course, if you have an electric field and you have charged particle, you will have an electric force. And then we end up in a situation like we've seen for the velocity selector. At equilibrium, you have the magnetic force that has to be perfectly balanced by the electric force. So what you end up is Q times VD times B equal to Q electric field H, so H for whole electric field. Okay, so this equation is similar to the velocity selector. So as you can see, the charge simplify, and you just obtain like the whole electric field has to be equal to the drift velocity times the magnetic field. So now for our conductor, so our conductor here at a width, which we call lowercase d. And if you remember the relationship between the difference of electric potential and the electric field, so you have delta VH, so difference of electric potential is equal to the electric field times the distance between the two sides of your conductor, so here to here. And this has to be equal to the drift velocity times the magnetic field times the distance between the two sides of the conductor. So if you remember the definition of the current, so you have the current is equal to the density of charge carrier times the cross section of your piece of conductors times the charge of the charge carrier times VD. So you can reverse the relation. So you became the drift velocity as a function of current and the density of charge carrier and the cross section of your piece of conductor, and as well as the charge of the charge carrier. So you can inject this VD into this relationship here, and you obtain the whole voltage, the whole like electric voltage difference between the two sides of the conductor. So between this side and this side here, and it's related to the so the magnitude of the current, the magnitude of the magnetic field, the dimension, the width of your conductor, the density of charge carrier, the charge of the charge carrier, and the cross section of your piece of conductor. So you can combine this by introducing the quantity RH, which is just the whole coefficient of your material, which is 1 over the density of charge carrier time the charge of the charge carrier. Okay, so that has some applications. So Hall effect is very often used to measure actually magnetic field, sorry, locally, because this like difference of potential, if you know like the characteristic of the material you use, is basically directly linked to the density, to the magnitude of your magnetic field. Yes, Boston, can you?
Sorry, what is RH and
So
what are,
RH,
what are N and Q?
So this is the Hall coefficient, which is defined here. Okay, so this is the density of charge carrier. So this is given in inverse cubic meter. And Q here, this is the charge. So the electric charge of charge carrier. Okay.
Okay, thank you.
All right, so if you look in the survey, so the official textbook of Physics 156, you will see a few examples where they use the Hall effect actually to measure the Earth's magnetic field. So it's very straightforward. So if you know the dimension of your piece of metal, and those are like constants that are given for a special material, if you know delta VH, you know the current and you know the dimension of your piece of conductor, you can directly derive the magnetic field. So now let's go back to very important application of magnetic force and field. So the first application I want to talk about is a cyclotron. So the cyclotron is a machine that is used to accelerate charged particle to very large energy. We have one on campus. It's used to make medical isotope. So how does it work? So we have a few schematic of the apparatus. So what you do is you have a region of very high magnetic field here, North Pole, South Pole. And you have like this half disk in which you can bend the trajectory of charged particle. And in between the two half disks here, you apply oscillating electric field that the purpose is each time a charged particle passes through this gap here, it will accelerate. Okay, so imagine you have a proton here, then when it passes here, for example, it is accelerated there, then it turns in the magnetic field, and when it goes there, the electric field has been reversed and it accelerates again in this direction. So each time it passes through the gap, it's accelerated by an electric field. Okay, so because of that, the radius of the trajectory and the velocity of your charged particle will increase. But as you remember from last time, the period, the orbital period, does not depend on the radius nor the velocity. So can someone remind us what is actually the formula for the period?
It's 2 pi m over qb.
Yes, exactly. So as you can see, does not depend on the radius and does not depend on the velocity. So whatever the energy, the kinetic energy of your charged particle, the period is the same. So that's why it allows you to use an AC voltage, like with a frequency that will be adapted to the particle you want to accelerate. Okay, so if you choose a frequency which is the inverse of the period, which is related to the particle you want to accelerate, then you can accelerate this particle to very, very high energy. So here's another representation of the same thing. So with less elements, but you can see you start from here and then you accelerate little by little. And at the end, when you have reached maximum energy that we will define together, you eject a particle and you can make it collide with other element or inject it like in tissues, for example, for proton therapy. And so this is a very, very important application of magnetic field cyclotrons. They are used, extensively used, and for medical application, for example, this is one of the main apparatus that you need for isotope creation or proton therapy, for example. So there is a picture that I took from the stairway, which is one of the first synchrotron that was built. So this was built in the 1930s, if I remember well. So how do we find the maximum energy of this cyclotron? Well, you have to use a relationship between the radius and the velocity of your particle. So if you remember last time, we've defined the radius of the trajectory, which is the momentum mv divided by qb. Okay, so this is the radius, the gyro radius of a particle in a magnetic field. If you go back to your cyclotron here, you see this has a maximum radius. Okay, so you cannot increase the energy to infinity because at some point the gyro radius will be larger than the machine. So that's actually when your particle is ejected from the machine. So if you inverse this formula, so when r is equal to r, so this is the radius of the cyclotron. Then you inverse this formula and you obtain a maximum velocity, which will just be qbr. So this you move up, qbr, and like lowercase r becomes capital R, the radius of the machine, divided by the mass of the particle. Now you can also calculate the kinetic energy at that point. So you just use the classic formula, 1/2 mv max square. And if you inject what we've just been calculated here, you just obtain q square, b square, r square divided by 2m. Okay, so there is no m square because like 1m is simplified with the m square here. Any question until now? It's clear for everyone? All right, so let's use this then in a first example. So we will use this cyclotron to accelerate alpha particle. So here are the given. So the alpha particle has a mass of 6.64 10 to the minus 27 kilogram and a charge of 3.2 10 to the minus 19 coulomb. And we want to find what is the period of revolution of the alpha particle and what can be the maximum energy in a cyclotron that has a radius of 0.5 meter and a magnetic field of 1.80 Tesla. 1.80 Tesla, this is a large magnetic field or this is a small magnetic field?
Large.
Very large magnetic field, yeah. Anything that is of the order of Tesla or higher is a very, very large magnetic field. All right, so let's try to solve this. So I will repeat the given. So given, so alpha particle has a charge of 3.20 10 to the minus 19 coulomb and the mass of 6.64 10 to the minus 27 kilogram. We are in a cyclotron, which has a radius capital R of 0.5 meter and a magnetic field B of 1.80 Tesla. So the first question is period of revolution. So for this, we can just apply directly the formula. So the period is given by 2 pi m divided by qb. Okay, so this is formula for gyro period. And we can just use directly the number we got. So it's 2 pi times 6.64 10 to the minus 27 kilogram divided by 3.20 10 to the minus 19 Coulomb times 1.80 Tesla. And in this case, we obtain 73 times 10 to the minus 9 second, which is the same as 73 nanosecond. Any question? No? So let's solve the second part. So the second question was, what is the maximum kinetic energy? So maximum kinetic energy. So we could directly use this formula here, but I will do it in 2 steps. So you get more details. So we can just start by calculate the maximum velocity. So the maximum velocity will be Vmax equal QB capital R divided by M. And we have everything we need. So we just need to input the numbers. So it's 3.20 10 to the minus 19 Coulomb times 1.80 Tesla times 0.5 meter divided by 6.64 times 10 to the minus 27 kilogram. And we obtain a maximum velocity of 4.30 times 10 to the 7 meter per second. Is it a large velocity or a small velocity?
Large.
Very large. Like, I mean, that's the speed of light is 310 to the 8 meter per second. So you see, like, we're a reasonable fraction of the speed of light already. So we're not there yet, but reasonable fraction. So now we can calculate the kinetic energy. So kinetic energy. So I will call it Kmax is equal to 1/2 mv max square, which is also the same as Q square B square capital R square divided by 2m. I can input the number and I will obtain 3.20 times 10 to the 19 Coulomb times 1.80 Tesla times 0.5 meter. Everything here is squared divided by 2 times 6.64 10 to the minus 27 kilogram, and I obtain 6.14 10 to the minus 12 joule. All right, so here we have a number. As you can see, these numbers still seem very small, okay? It's 10 to the minus 12 joule. While for protons, this is actually a pretty big energy. So we need to use another unit to actually realize that this is a quite big energy for such a small particle. So I will remind you what is the electron volt. So you normally have seen that already with Professor McWilliam in the electricity part. So the electron volt is defined as the kinetic energy that an electron gains when accelerated through a potential difference of 1 volt. Okay, so if you assume that only the electric force is acting on the electron, you have like the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. So the difference in kinetic energy, this is the change of energy, and this is minus Q times delta V. So if you assume delta V equal 1 volt, and the charge is minus E, so E, you obtain 1 eV. So 1 eV is equal to 1.6 10 to the minus 19 joule. So you can write this like there is 1.6 10 to the minus 19 joule per EV. Okay, so this is a technique that I use. So when you deal with units, so you realize that you are dealing in joule per EV. So if why do we use EV for particles such as electrons and protons? Is well, it's not very useful for the joule is not very useful for particle physics. So you end up with quantity like we just calculated of the order of 10 to the minus 12 joule. And while Vmax 4.3 10 to the 7 meter per second, it's like more than 10% of the speed of light. So that's actually very, very, very fast. Okay, and 14% of the speed of light is small for macroscopic standard. Like, I mean, if you move your hand in air, you have much more than 10 to the minus 19 joule. But for one proton, it is actually huge energy. Okay, so that's why particle physicists are using a more appropriate unit, and this unit is the EV. Okay, so what is the kinetic energy in MeV of the alpha particle of the previous question? Well, so we add Kmax that was equal to 6.14 10 to the minus 12 joule. We know you have 1.602 6 10 to the minus 19 joule per EV. So if we want Kmax in MeV is Kmax in joule divided by 10 to the 6, and the 10 to the 6 because here we're talking of MeV, so million, so which is equivalent to 10 to the 6 times the definition, so 1.6 10 to the minus 19 joule per EV. So we see the joule will simplify and the EV will come up, and if you do it, you will obtain an answer of 38 mega electron volt. So you see now you have 38 million of electron volts, which is a large number, and for a proton, this is a very, very large energy. Okay, so that's why in particle physics, they always talk in EV or MeV or any derived unit of the EV, because for such small particle, you need to use a unit that is adapted to that. Okay, so when you get 14% of the speed of light, sure, macroscopically, it's not a huge quantity of energy, but for a proton, which is a very small particle, this is actually a big deal. And 38 MeV, it's quite a large energy for a proton. Any question? Clear for everyone? All right, so the cyclotron, this is a classic exercise for assignment or for tests. Okay, so before physics 156, we were teaching physics 155, which was electricity and magnetism and circuit. So the electricity and magnetism part were very similar to physics 156, and the cyclotron was in like every second midterm. Okay, this is such an important application that you are guaranteed you will either get it in assignment or in module test. Same thing for the second application, which is a mass spectrometer. So mass spectrometer are highly used to identify elements or like atoms of molecules. That's what you have in a gas, or what you like in a gas or in a chemical, different type of chemical that you vaporize and ionize, and then you want to identify what you have in it. So it's a very, very efficient way to identify elements of molecule. So how does it work? So you have your source of particles. So you will ionize them, and then you go through a velocity selector. Okay, so what we've seen 2 lectures ago. So you have an E cross B filter, and you get a given velocity of particles that goes through the filter. And so here, the velocity the selected velocity is just equal to E divided by B. And then finally, you enter a deflection chamber, and depending on the type of particle, the radius of curvature here will change. Okay, so that will depend on the ratio Q divided by M. So you can measure this with a particle detector, and if you are able to measure the radius, because you know the velocity you have due to your velocity selector, then you can calculate the Q over M ratio and then identify the particles that were entering in your mass spectrometer. Okay, so it's very, very widely used to identify elements in labs or in industry or for medical application as well. So here's a picture of the first mass spectrometer that was built. So it's but the same principle. So you have a cathode here that you use so here's where your charged particle. They are deflected by both an electric field and a magnetic field here. So like that's your velocity selector. And at the end, you can measure the deflected electron beam, and that's how they were able to actually measure the charge of the electron. So let's use this in a real world example now. So here's the exercise. So a particle passes through a mass spectrometer. So we have a velocity selector. So at the end of the velocity selector, in the velocity selector, sorry, you have an electric field. You have an electric field that has a value of 9.55 10 to the 4 volts per meter. And you have a magnetic field that is the same in the selector and the deflection chamber. So magnetic field here is the same as here, and has a value of 0.95 Tesla. And we have a particle that strikes the detector 2.88 centimeters away from the entrance of the deflection chamber. So this distance here will be 2.88 centimeters. So we want to calculate the charge to mass ratio, and from there we want to calculate the mass and identify the elements if the particle is singly ionized. So this is a very important information. All right, so let's solve this. So first with the given. So mass spectrometer. So the selector, the electric field is 9.55 10 to the 4 volts per meter, and the magnetic field is equal to 0.950 Tesla. And we know, like, the particle strikes the detector 2.88 centimeters away from the entrance of the deflection chambers. That means like 2 times the radius, the gyro radius is equal to 2.88 centimeters. So here, capital R, this is gyro radius. Okay, so here you have to be very careful. This is 2 times the gyro radius, okay? You start from here 0 and you strike 2.88 centimeters away. So the radius is obviously half of this distance here. So that's a common mistake, like do not realize that the number that is given to you is twice the radius. So now let's solve the exercise. So first of all, we want to calculate the charge to mass ratio. Charge to mass ratio. So we will go in 2 steps. So first of all, we need to find the velocity of the particle. So this is given by the velocity selector, and it is just E divided by B. So we obtain 9.55 10 to the 4 meter per second divided by 0.950 Tesla, and that gives us a velocity of 1.01 10 to the 5 meter per second. Then we need to find the charge to mass ratio. So charge to mass ratio so mathematically it means we are interested in Q divided by M. So we have to remember what is the gyro radius. So the gyro radius is mv divided by qb. We just calculated v. So this is r is equal to m divided by qb times e divided by b. So we can get the charge to mass ratio. We obtain q over m is equal to 1 over rb. So actually I will use capital R because that's what I was using here. Times E divided by B. And I know everything, so E divided by B. So this is just the velocity I just calculated, so I can just actually keep it as 1 over RB times V. So this is 1 over 2.88 10 to the minus 2 meter divided by 2 times 0.95 Tesla times 1.01 times 10 to the 5 meter per second. And I obtain a charge to mass ratio of 7.348 10 to the 6 Coulomb per kilogram. Now we want to identify the particle. B, identify particle assuming Q equal E. So why Q equal E? This is here singly ionized, mean Q equal E. And so we have the value of Q over M. So Q over M equal, so 7.348 10 to the 6 Coulomb per kilogram. Q equal 1.6 10 to the minus 19 Coulomb. So we obtain M equal to Q divided by 7.348 10 to the 6 Coulomb per kilogram, 1.60 10 to the minus 19 Coulomb divided by 7.348 10 to the 6 Coulomb per kilogram, and we obtain a mass of 2.18 10 to the minus 26 kilogram, 26 kilogram. So now you can use the proton mass. So M proton is what, 1.67 10 to the minus 27 kilogram, which is roughly equal to the mass of the neutron as well. So you know, like this element here has 13 nuclei. Okay, how do I know that? Is the number of nuclei, n nuclei is equal to M divided by MP, and you will obtain this 13 nuclei. So we have two possible elements if you look in your periodic table of So it's either 13 nitrogen, which has 7 proton and 6 neutron, or carbon 13, which has 6 proton and 7 neutron. Okay, so we have reduced, we know like the particle that been through the mass selector, it's either this unstable nitrogen or this carbon 13. All right, any question? So let me remind you, those two examples we've been through together, they are classic examples. So you are guaranteed to have one of those in either assignment or module test. Like, I mean, the wording might be slightly different, but the spirit of the calculation you have to do will be almost the same. So there you work, though, like you really need to work those two examples because they are very, very important. Okay.
I have a question. Can I see just the last slide? Just have to copy one number. A little bit. No, it's like Q.
So like the entire slide.
Yeah. Okay, perfect. Thank you.
All right, so we just finished the first chapter and we'll jump into the second chapter, sources of magnetic field. So for this second part of chapter 28, so remember the charge to mass ratio. We just calculated it, the maximum velocity, the force on a straight wire, and finally the torque on a current loop. Okay, so those are the formula you need to remember. All right, so now let's jump to the.
Can I ask a quick question, quick?
Yep, go ahead.
Just in that first, the charge to mass, is the BO, is that the...
All right, so here is a slight difference. So here in the exercise we did, we assume like the magnetic field was the same everywhere. Okay, B and B0 were the same. So in the exercise, I just use B because they're the same. You have machine where the magnetic field is not necessarily the same in the velocity selector and in the deflection chamber. So in this case, you have to use the two, B and B0. That's why you have here B0 and B.
Okay, so B is inside the chamber and then BO
so
is
B
in
is the velocity selector and B0 is the deflection chamber.
Okay, thank you.
At the end of the slide, you have some complementary materials, so YouTube videos to some MIT lecture that are very good to complement what we've been studying together. All right, so now let's move to the next chapter. Which is sources of magnetic field. So in the stairway, this is chapter 29. There will be two lectures, so this one and the next one on it. So hopefully we can catch up with like the delay we're taking. So first of all, today we're gonna see the Biot and Savart laws, and we'll just study the magnetic field due to a thin straight wire. And finally, we'll try to derive the force between two parallel current wire. All right, so by the end of this section, you should explain how to derive a magnetic field from an arbitrary current line, calculate the magnetic field from the Biot-Savart law in specific geometry, explain how parallel wire carrying currents can attract or repel each other, and calculate the force of attraction or repulsion between those two wires. Okay, so in chapter 28, we have seen that the force on moving charge due to the magnetic field. So you have a force that is exerted on this charge unless the velocity is parallel to the magnetic field. So this force is given by the formula F equal QV cross product with B. And the macroscopic consequence was if you have a magnetic field, you have a current carrying wire in a magnetic field, the force exerted on the wire is IL cross product with B. We also know that like opposite charges plus minus attract each other and like charges plus plus or minus minus repel. So that was like electricity part. We have the kind of same thing for magnetic field. So north south pole attract each other, but north and south they repel each other. So the electric or magnetic force on a charge or the pole of a magnet is due to the presence of the electric or magnetic field. Note that static electric charge are unaffected by static magnetic field, but static electric charge are affected by changing magnetic field. So that's what we'll see in the next chapter, induction. So for now, just remember that static electric charge unaffected by static magnetic field, but static electric charge will be affected by changing magnetic field. All right, so first of all, the Biot and Savart law. Ortsten in 1820 showed that an electric current produces a magnetic field. So the shape of the magnetic field line along a long wire can be found by compass or iron filling. Like iron filling or compass, it will align with the direction of the magnetic field. So if there is no current passing through the wire, they orientate around the Earth's North Pole. But if you have a strong current, then you create a magnetic field, and all the compass needle will align with the magnetic field. For this, there is a demo.
First, look at the single current wire. It's coming towards you and it goes into, of course. It is a wire that goes like this, and the reason why you see it here is, of course, we have to get the current in somehow. But it really is a wire like this. And this platform I'm going to show you. So I'm going to put some iron file around this. These are magnetites, and when they see a magnetic field, they will try to orient themselves in the direction of the magnetic field. So you're going to see these circles. But appreciate the fact that you need huge currents for this. Hundreds of amperes we do. That's why we have a car battery here. Remember, that was capable of delivering many hundreds of amperes. So I close the current now. I tap, and you can see the circular configuration. I hope you can see that. Looks like circles. I want to do the same now, which is a little bit more exciting.
All right, so the second part of the demo will be for another lecture. So as you have seen, when you have current flowing through a wire, so it's like hundreds of amps, then the iron filling, which act like small magnetic needles, they align with the magnetic field, and you see this circular pattern forming. So it was a experimental proof of the creation of magnetic field by electric current. So that was done the first time by Ørsted, and it was like compass and current carrying wire. And what will be discovered later by other physicists is actually the source of any magnetic field is an electric current, so moving charges. So in fact, any moving charge induces a magnetic field, and so this is current in wires, but it's also electron orbiting around nucleus in atoms, and that's how you can explain the existence of magnetic materials. So before we jump into the mass, so how do you find the direction of the magnetic field? So again, we have to use a right-hand rule. So if you have a current carrying wire, so here the current is flowing upward. So you take your right hand, you surround the wire, and your thumb has to be in the direction of the current, and the magnetic field is actually following your fingers. Okay, so in this case, what you find if you use a right-hand rule is on the right side of the wire, the magnetic field is going into the screen, and on the left side is going out of the screen. So if you want a 3D representation, that's what you have here, and you have those circular magnetic field lines, and that's what you could see in the demonstration here. So you have those circular magnetic field lines. So now how does it work? So following Ørsted, the experimental observation of Biot and Savart were used to quantify the magnetic field dB at point P outside of a wire element of length ds carrying a current I, so ds vector oriented in the direction of the current. So basically you have your point here, you have your small element here. So you have to define vectors that goes from your element to your point P. And basically what was found is the magnetic field is perpendicular to both ds pointing along the current and the unit vector r. So it will be perpendicular to this vector and perpendicular to this vector. It will have an intensity dB, which is proportional to ds, proportional to the angle between r and ds. Sorry, here should be an s. And inversely proportional to the square of the distance between the wire element and the point of interest. So here should be an S as well. Sorry about that. And so therefore the Biot-Savart law is dB equal mu 0 over 4 pi IDS cross product divided by R square. Okay, so now you can put this on the schematic. So you have your element ds, and you can consider 2 point P and P prime. And as you can see with the cross product, so the current is flowing like upwards here. So you can use the right-hand rule actually to find that directly. But because of that, you have the magnetic field here pointing into the page. And at point P here, it will be out of the page. So then you can make comparison with the Coulomb law. So here is a Biot-Savart law, where mu 0 is the permeability of free space, which is actually very convenient because you can just write it as 4 pi 10 to the minus 7 Tesla multiplied by meter divided by amps. And you can see there is some similarities with the Coulomb law you've seen with Professor McWilliam, whereas the electric field was 1 over 4 pi epsilon 0 dq divided by r square, where epsilon 0 was the permittivity of free space. So you see in both cases, the electric field or the magnetic field, they are inversely proportional to the square of the distance from the source to the point of interest. So they decay in the same manner. Okay, so the further away from the source you are, the weaker is the magnetic field in case of magnetic field. All right, so now we're going to try to use this Biot-Savart law to calculate the magnetic field created by a wire. But before that, do you have any question? No? So this formula here is very important to remember or to recognize, okay? This is a Biot-Savart law that explains how you can relate magnetic field to flowing current. So now let's use it to calculate the magnetic field due to a thin straight wire. So I warn you here, it will be a bit mass intensive. The demonstration will involve calculation of integrals that are a bit hard for you this year because like you haven't seen the details in math yet. What I want you to remember is the spirit of the demonstration. The details of the math, you'll learn them in greater detail later on your math course, and you'll see them again next year. But I just want you to fully understand how the principle behind the calculation. And in test or in assignments, you won't be asked to derive the formula, but you might be asked to explain how the calculation is done. Okay, the principle of the calculation, not the detail, but the principle. So we have to start from the Biot-Savart law. Okay, so before we calculate the thing for a wire, we just take a small element of wire here, ds, and here we consider 3 points, A, B, and C. And here's the Biot-Savart law. So for you, where will be the greatest magnetic field? At A, B, or C? And why?
Is it A?
So if it's A, try to justify why.
Because it's closer to the wire than B and C.
So that could be a justification, but look here, you have a cross product.
B?
Yeah, it would be in B. So why it's not in A? Because you see, if you plot the R vector here, ds, here it should be ds, sorry. ds and R, they are parallel to each other. So the cross product is 0, so it cannot be A. So for B and C, so we have RB like that, and RC like that. So they're not parallel, so the cross product won't be 0. Okay, but in B, the distance is much smaller than in C. And because of that, the magnetic field would be greater in B. Does that make sense for everyone?
Yes.
All right, so now that we know that for a wire, you have to actually consider not only one portion of the wire, but all the small section of the wire. Okay, so if you're interested in a magnetic field in point B, for example, for sure, the main contribution will come from the one that is just in front of it, but you have to take into account the contribution of all the small element of wire. Okay, so each element of wire has its own contribution dB, but if you have to cut all this wire in small pieces, each is carrying a current. So again here, ds, not dl, sorry. I will update the slide on Canvas so you don't have this typo coming up everywhere. And so you have to cut the wire into small pieces and you have to sum all those small elements. Okay, so if you cut in small pieces like I did here, you have to make a summation of all the current element of your wire. Okay, and because those small elements are taken like infinitesimally small, so you have ds going to 0 and your sum here becomes an integral. Okay, so to calculate the magnetic field at a given point, you have to make the integral over the entire length of the wire. Okay, so that is the spirit of what we're trying to do right now. Okay, we will take a piece of straight wire and we'll try to calculate the magnetic field by making this integral. So here's a configuration. So we take a piece of wire of length 2 lowercase a, and we are interested in calculating the magnetic field here at point P, which is at a distance lowercase r from the middle of the wire. Okay, so obviously here we're gonna use cylindrical coordinates because it has a cylindrical symmetry. You can turn around the wire, doesn't matter. Like, I mean, if I'm at a distance lowercase r from the wire on the right, or at a distance lowercase r just in front of the wire, the magnetic field will be the same. And that's what you could see from this picture, okay? If we calculate here the magnetic field, or here the magnetic field, or here the magnetic field, the only thing that changes is the vector, the direction of the vector, okay? But if you use cylindrical coordinates, the vector is the vector associated to the angle, and it doesn't matter where you are, okay? That will be always along phi hat, the unit vector associated to the angle. Does that make sense to everyone, the use of cylindrical symmetry here? Yes, all right, so now we're gonna take a small piece of this wire. Here we call ds, which is along the z-axis. Okay, so this is the z-axis. So ds is just dz k hat, which is a unit vector along the z-axis. And this small element here of wire, it has a distance capital R from point P of interest. Okay, so R in cylindrical coordinates, it will just be lowercase r along r hat, so your unit vector that goes from the middle of the wire to the point of interest, plus z, not z hat, but k hat. And from this capital R vector, we can define capital R hat, so a unit vector, which is just R vector divided by the length, so capital R, which is the same as lowercase r square plus z square. Okay, so this is the case for every small element ds of your wire. So now this element ds creates this small magnetic field. Okay, and we want to calculate the intensity of this magnetic field. So it's something that has to be taken into consideration here. Is if you come back to your schematic originally, so this, you see you have an angle theta here. Okay, So this, if you take the Biot and Savart law here, you see like the R hat, you have to make a cross product with ds. Okay, so your ds is actually in this direction, and you want to make the cross product with R hat here. So the only component that will matter will be the components that are actually perpendicular to R hat. Okay, the components that is parallel to R hat will not matter. So when you use the Biot and Savart law here, you will end up with a cross product that of R hat cross K hat, which will give you phi hat. So you already know that the magnetic field will be go inside the page when you just use a right-hand rule, but actually when you do the cross product K hat with R hat, you also find this will be along the phi hat direction. So now the magnitude of the magnetic field that is created by the magnetic field. So here, sorry, it should be capital R hat. Okay, we go from the element to the point P. So this capital R hat, you have to make the projection on lowercase r hat, so the unit vector associated with spherical coordinate. And you know that's the only component that matters. So when you make this projection, you have a cosine that appears and you obtain I dz. So this is ds cross r, cross capital R hat. So this is just cosine theta. So this is just the parallel. So this is a perpendicular component. Okay, so this is parallel to lowercase r hat, and that the only component that matters in the cross product. So you obtain k hat cross lowercase r hat, and this is equivalent to phi hat in cylindrical coordinates. So now for your wire, obviously you have to make the integral over all the small elements ds. Okay, so you start from the bottom, you go to the top, and the integral you end up calculating is, so b vector, so we know it will be along phi hat, so it's mu0 over 4 pi that come from this term, the integral over the whole length of the wire of I cos theta dz over r square. Actually, this is yeah. So that's the integral you have to calculate at the end. Let me check something. All right, I will correct this on. So here it should be capital R square. Sorry about that, but sometime when you have the same letter everywhere, you lose the lowercase and the capital cases. So that's the integral you have to calculate. So this is complicated mathematically. I won't go into the details of it, okay, because this induces changes of variable. I will post, for those of you who are interested on Canvas, the details of the derivation, but I don't want to do this in here. So what you have to remember is the spirit of the derivation. So you take small elements and you have to be able to like show that B is actually an integral of all the wire. And you see here, you have to take into account that you have a changing angle from the top of the wire, from the bottom of the wire to the top of the wire. So this integral is complicated because this capital R here depends on Z, okay? So when you do the integral, this integral here, you should not forget that this R square here depends on Z, okay? And the angle theta also depend on Z. So this is a complicated integral, and just to solve it together would take a very long time, and this is not a math course, so I will just give you the answer. Okay, so if you do this integral that will involve change of variables, you will obtain that the magnetic field created by this piece of wire of length 2a is mu0 I divided by 2 pi times a, okay, so half of the length of the wire, divided by lowercase r, so the distance from the middle of the wire to the point P of interest, times the square root of lowercase r squared plus a squared, so half of the length square, along phi hat, because you are turning around the wire. Okay, so that is what you need to remember. And how you get there, the only thing you need to remember is you have to make an integral over the entire wire, and the contribution depends not only on the distance to the point of interest, but also the change of angle from the bottom of the wire to the top of the wire. Any question?
So if we had to do a problem like that, would we just be given one lowercase r value to use?
Yes. So we will never ask you to derive the entire integral and stuff. So basically, a typical problem, we tell you like you have a wire of length, I don't know, 10 centimeters, and we tell you calculate the magnetic field vector at 10 centimeters away from the center of the wire. So here you have to remember that if we give you the entire length, A is just the entire length divided by 2. So that will be the thing to remember.
Okay, and then where would we get the current for that? Like I.
So I would be a given as well.
Okay.
Okay, and it would be for you, you also have to realize, so in this case, in this formula, the current is flowing to the top, okay, from the bottom to the top. If the current is flowing from the top to the bottom, what will happen to this formula?
I think the phi hat will change.
Yeah, you just obtain a minus sign, okay? You can always find the direction with your right-hand rule. So current flowing up, going in, coming out on the other side, going in on the right side, coming out on the left side. If it's going down, you go this way. So it's going in the left side and coming out on the right side. Okay, so the direction of the vector, you can always find with the right-hand rule. Okay, which is easier. Personally, I find this easier to find the direction using the right-hand rule than instead of remembering all those cross products of unit vectors. But if you prefer to learn all your cross product, go ahead, it works too. All right, so what we have to remember, so now we'll study infinite line. So for infinite line, so the magnetic field line are obviously circular and centered at the wire. They are identical in every plane perpendicular to the wire. The strength, and this will show in the next slide, decrease as 1/r, and the direction is given by the right-hand rule. So again, right-hand rule, thumb around the direction of the current, and magnetic field line direction is given by the direction in which your finger are curling. So let's define this for an infinite straight wire. So for an infinite straight wire, so A goes to infinity, okay? Means like r squared plus a squared is roughly equal to a squared, okay? Meaning that r squared plus a squared roughly equal to square root of a squared roughly equal to a. Now you see where I want to come. So if I have square root of r squared plus a squared roughly equal to a, then I have b equal mu 0 I over 2 pi a over r times a, okay, phi hat. A simplifies with a, and I obtain a magnetic field strength, which is proportional to the current and inversely proportional to the distance. Does that calculation all right for everyone?
Yeah, could you go back to the other slide just for like 1 second? Okay, yeah, good, thank you.
All right, so let's use this in a classic example. So we want to find the magnetic field at a distance of 1 meter and at a distance of 4 meters from a wire carrying a current of 1 kiloamps. So we want the magnetic field. Okay, so this is a vector. Magnetic field is a vector quantity. So in an exercise, if they ask you magnetic field and not magnetic field magnitude, you are expected to give a vector answer. So the given so I equal 1.0010 to the 3 amps. So this is 1 kiloamps. So upward. And we want, the question is, so B at R equal 1 meter and R equal 4 meter. So right hand rule. So B turns. So as you can see here, if you use a right hand rule, see anti-clockwise. Around the wire. And if I use cylindrical coordinates, okay, this anti-clockwise direction is what we call along the phi hat direction. Okay, just for. So if you just write B turns around, anti-clockwise around the wire, this is good enough to get full mark in an exercise. Okay, you have given the direction of the vector. So now we want to calculate the magnetic field. So the magnitude is just given by mu 0 I over 2 pi r. And it will be along phi hat. So for r equal 1 meter, we have B equal 4 pi times 1 times 10 to the 3. Sorry, 10 to the minus 7. 4 pi 10 to the minus 7. So this is mu 0 amps divided by 2 pi times 1 meter. So the good thing is the pi simplifies with pi, the 1, so phi hat.
Why is it 1 times 10 to the negative 3 amps, but in the given it's 1 times 10 to the 3?
Plus 3.
Okay.
Thank you very
Thank
much. So we have a B, which will be equal to, so 1/2, 4 divided by 2 is 1/2, 10 to the 3 times 10 to the minus 7, so it's 10 to the minus 4, phi hat Tesla. For R equal 4 meters, same formula. So B equal 4 pi 10 to the minus 7 times 10 to the 3 divided, so phi hat Tesla, divided by 2 pi times 4. So 4 pi, and Here it's 2. Sorry, it's not 1/2. This is 2. Here we have 1/2 times 10 to the minus 4 phi hat Tesla. Does that make sense for everyone?
Yeah.
All right, so now let's try to find the force between two parallel currents. So for this, I will just start with a demo.
The two wires run vertically. This is one wire, and this is the other wire. And when I run a current in the same direction, then they will attract each other. And you will see that shortly. 3, 2, 1, 0. See, they go towards each other. I will do it again. Now, if I run the currents in opposite directions, they will repel each other. Now I run them in opposite direction. They repel each other. I'll do it again. 3, 2, 1, 0. They repel each other. The reason why I showed you this demonstration is a different one. What I want you to appreciate that if I have this conducting plate of aluminum, it's a conductor, and I put that in between the two wires, and I repeat the experiment, that exactly the same thing will happen. And that tells you that magnetic fields are really very different from electric fields, because electric fields would be heavily affected by a conducting sheet like this. Magnetic fields are not. So what I'm going to do now is I'm going to put this plate in between, and then I'm going to again put the currents in opposite directions, and so you will see the wires repel each other as if the plate were not there. 3, 2, 1, 0. There you go.
All right, so what you've seen here is when you have two parallel currents, the current in each wire will generate a magnetic field. The magnetic field will exert a force on the current carrying wire, and parallel wire must therefore exert a force on each other. So let's try to find the direction of this force. So consider wire 1 here with I1. So you use the right-hand rule, and you see like you have the magnetic field here at the position of wire 2, which will be in this direction. Okay, so the magnetic field created by the first wire at the position of the second wire. Now you can use like the right-hand rule again. So IV cross B, and you see like if you use the right-hand rule, so thumb is the direction of the current, finger is the direction of the magnetic field. The force is given by the direction you push with your palm, and you see like the resulting force will be in this direction. You can do the same for the force created by the second wire on the first wire, and the force here will be in this direction. So just by using right-hand rule and what we know about electric magnetic field created by current, we know like if the current flow in the same direction, they will attract each other. Okay, anyone can understand that? If you have question.
Dr. Cadell, I had a quick question about the right-hand rule. I apologize. When I'm holding the hand up to my face, is my palm towards my face or is my palm towards the computer screen?
It depends on
like for setting it up.
It depends on the vector you're considering. So if you use for this case, so put your thumb in the direction of the current, your right thumb in the direction of the current, then the magnetic field must go inside the screen. Okay, so you end up, if you look at me, you end up with your palm that will push in this direction. Okay, and that's the direction of the force.
I think it's so confusing because you're mirrored. So I think you're maybe pushing the
okay,
my video I think is mirrored, but no, it's all right. I'll figure it out. Thank you so much.
Okay, so yeah, that's the thing. Like when you teach online, sometimes the camera does weird thing. In person, it would be much clearer for sure. But yeah, use your right hand rule, thumb direction of the current. Your finger must be going inside the screen given the direction of the field. So you're in this specific case at wire number 2, your palm must push toward wire 1. Okay. All right, so how you can see this mathematically? So this very quickly, actually. So you know, like the force per unit length created by a wire is F2 divided by L. So what we've seen last time is I2 times B1. B1, the field created by wire 1 at the position of wire number 2. So side view, top view. From there, we just seen that the magnetic field B1 is mu 0 I1 divided by 2 pi R between the distance between the two wires. So you can just inject this. So you have F2 over L equal mu 0 I1 I2 divided by 2 pi R. And if you use the right hand rule, again, same direction, attractive, opposite direction, the force will be repulsive, and what you've just seen in the demo. So next lecture, we'll try to use that to calculate some forces on different wires. But I'm already over time, so I will stop here for today. And if you have questions, I'll be connected for the 10 to 15 next minutes. So thank you very much, and I see you on Wednesday.
Wait, so sorry, what's L in that equation that you just said?
L is just a length, okay, and it's just to get a force per unit length. So if you remember last lecture, we had been calculating, so if I can find the slide. So this example, no. Yes, so if you remember this example last time, a long rigid wire, we were not given the length of the wire. So I had called it capital L at that time. And we just had divided the force by this unknown length, and we had obtained a force per unit length. Okay, so here in here, I just use L instead of capital L, but that's the same thing. We just get a force per unit length because we are considering infinitely long wire. So by definition, we don't know the length of the wire.
Gotcha. So it's just the length of one wire.
Yeah.
Do both wires then have to be the same length?
Well, they're infinite, so by definition, doesn't matter.
Oh, okay. Okay, thank you.
Thank you, Professor Kudal.
No problem. If you have any question, do not hesitate to contact me.
Hi. Hi, Professor Kudal.
Yep, go ahead.
I was wondering how should we explain when we use the integration of the biosignal rule? Like, what would be expected for that explanation?
So for the explanation, basically, you have to be able to tell that when you calculate the magnetic field created by a wire, this is an integral over the whole length of the wire, because each small piece of wire has a contribution to the total magnetic field.
Okay, thank you so much.
Yeah, sorry, I have a question regarding something about the permittivity and permeability. I don't know if it's a mistake, but if you go to the slides.
There might be some typo. It happened, you know, like if you found a typo, thank you very much for pointing it out.
Yeah, so the probability of free space, I think it's 10 to the minus 12.
Exactly. There is a 10 to the minus 12 here missing. Thank you very much.
No problem.
Wait, where is this one?
So epsilon 0 for the Coulomb law, there should be a 10 to the minus 12, 8.85, 10 to the minus 12.
Yeah.
So I'm still here for like 5 to 10 more minutes. So if you have questions, do not hesitate.